Good day to all. I'm Bhavani Shankar, Assistant Professor at the Interdisciplinary Center for Security, Reliability and Trust, SNT for short, at the University of Luxembourg. And it's my pleasure to welcome you to this presentation on unlimited sampling for FMCW radars, a proof of concept at the Radarconf' 2022. The paper is co-authored by Dr. Fuyan, Dr. Alai, Professor Bhandari from the Imperial College, myself, and Professor Utterston. Without much ado, I would hand over the presentation to the first author, Dr. Thomas Fuya, for the details. Thank you.
So, hi everyone, and thanks Bhavani for the introduction. So, here in this talk, we're going to try to answer one simple question, which is, can we use unlimited sampling to solve some of the issues, some of the limitations that we might encounter in classic acquisition? So to that end, we're going to look at what is the unlimited sampling way of doing the acquisition and what happens to the processing. So for the outline of the talk, first we're going to review quickly our signal model, so what is the radar that we use, what is unlimited sampling, and then I will do a live demo of what we managed to do up to now, and then I'll finish with some future work. So here the signal model. So what we're using here is an FMCW radar, so frequency modulated continuous wave. So essentially, and you might all be familiar with it, what it does, it transmits a chirp, so a signal whose frequency increased linearly, and you get the signal back with a delay, okay? But here, instead of measuring the whole signal for according to its large bandwidth, thanks to the coherent demodulation or stretch processing, you are able to translate this time delay into a frequency shift. And so this is what you see here. So the received signal in the end is a complex exponential whose frequency is related to the range of the target. So what it means is, if you have somebody here at a certain range, you get a certain frequency, and if he moves away, the frequency increases. Okay? And if you got more than one target, you just have the sum of the two signals with the two corresponding frequencies. Okay? So now, what about the acquisition? So because here we've just seen how the radar works, but now you need to acquire the signal. So let's say that this is what you have, okay? So now you need to measure it. So one thing that you can do is use an ADC, so analog to digital converter, which will digitize the signal. And so this has a specific dynamic range, so and if you go over that, you saturate, and it has a certain resolution. And so if you apply this, so if you digitize this signal according to this, you get, for example, that signal, okay, that discretized signal. So of course, maybe that may be sufficient, maybe in other cases you want to have a better resolution, so you go to high number of bits, so here, a higher resolution. But again, if you want to go to that, then you will generate more data, okay? So it might be complicated in some applications. So this is for one target. But then what happens if you have more than one? So here, let's say that this is what you have. So the same situation that I showed before. And so if you were to use the same the first ADC that I showed you, you get a signal like this one. So you see that essentially the big target, so here the bigger signal is well represented, but the second one, not so much. In fact, if you compare to the previous signal, which is this one now, these two are almost identical. And so in a way, the second smaller target has been incorporated within the quantization noise. So here, between this and this, it's almost the same. And so again, one solution is just to increase the resolution, but then you have more data that you need to acquire. So you need to have an ADC that is more costly, that requires more power. Okay? And so this type of issue can actually happen in radar because, as you all know, so the power of the target or the amplitude of the signal is dictated by the radar cross-section. And even targets that are similar, that are at same range, depending on the angle at which you observe them, the power might vary dramatically. And so maybe, if you have more than one target, some will have extremely large amplitude and other small one. And so your ADC will need to accommodate that dramatic change of dynamic. Another thing is the power of the target changes with the range. So which also creates signals with really large dynamic range. Okay, and so your ADC needs to be tailored to this, which in some case might be really challenging. So for example here, using this radar, so this is what we've done in the paper, what we show is, for example, this radar has a strong coupling between the transmit and the receive, and so when you want to measure actually the cars, what you first measure is the coupling of the two radars, and then the actual signal that you're looking for here is of several order of magnitude lower than the signal that you're measuring. And so here what happens is you measure something that you don't really care about with a really high resolution to allow you to then get that back. So it is not really efficient. And so to that end, now we want to use unlimited sampling. So we see that the main issue that we have is we need to have a large dynamic but also a high resolution. Because if we lower the dynamic with our classical ADC, then we will saturate. So we will lose information. But then what can we do to lower our dynamic and to keep while keeping a high resolution? So what unlimited sampling proposes to do is to fold the signal. Okay? So lowering the dynamic of the signal by folding it around a certain value. And so what it does, and I will show you a picture afterwards where this will make more sense, is that now the acquisition is not constrained by the dynamic because the signal will always fold. So for example, this is what we had before, okay? And now if you do the folding, so the unlimited acquisition, you get something like this. So you just need to tailor your ADC to that dynamic, and if it goes over, it just comes back here. So again, this looks like really cool, but the next obvious question is, if one were to have these ADCs, okay, can you still reconstruct the signal? Otherwise it's useless, okay? And the answer to that is that actually you can. And so this is what has been shown by Ayush Bandari, which is one of the co-authors of this paper. And he showed in previous publication that, and so here I won't bore you with the detail of the theorem, but essentially what the theorem says is, if your signal is band limited and that it is acquired with a slight oversampling, then you should be able to reconstruct the signal perfectly. So it means that just by slightly oversampling by this coefficient, you should be able to recover everything. And what is interesting is that this coefficient doesn't depend on the dynamic of the folding. So either you fold on using this dynamic or this one, you don't need to change your oversampling factor, okay? Then the next question is, okay, it's nice to know that you can actually reconstruct it, but can you reconstruct the signal efficiently, okay? Because there's no point in lowering the complexity of the acquisition to get something that is overly complicated to reconstruct. And again, here, in this case, you can show that you can use a simple iterative algorithm, okay, to reconstruct the signal. And so here, essentially, by just following these steps in a deterministic way, so you're not using some kind of convex algorithm, you just process this data according to this, you should be able to recover your signal, okay? And so now, if you go back to our first issue, and to the theorem that I've shown you, so we know that FMCW radar signal are band limited, okay? And because we have a simple iterative algorithm, we should be able to do real-time processing. And so this brings us to the next step of this presentation, which is a live demo. We should be able to do it live. So here, let's go for the live demo. So what I'm using is a simple, here, K-band radar, okay? So now I can show the data live to you. This is the live data from the radar. And so what you see here is the INQ signal. This will be the folded measurement, but for now the dynamic is so small that there's no folding happening. The reconstruction, and here just an FFT over the two, just to get an idea of the range. So now if I take here one target, this is what I get. So as expected, here you've got a sine wave. here you see the folded measurement, and here the live reconstruction. And so you see that these two are identical. And so now if I move around, you see the signal with the frequency that increases or lowers depending on the range. And you see that I'm able to do live reconstruction. Okay? And so for example, I can also change here the power that you get by changing the RCS, by moving the target around. Okay? And you see that everything works. Okay? Okay, so now let's bring this back to the measurement that I showed you earlier. So what we showcased in the paper. So what we want to measure is the position of the two cars using this radar, which has a strong coupling between the transmit and the receive. And so here, this coupling is exactly what you see here, and the signal of interest is of a smaller order of magnitude below it. And so if you were able to do, because for now we do the classical acquisition and then do the unlimited sampling in software, but if you were able to do it practically, you would get this signal, be able to do the reconstruction and get exactly the same signal. But if you were to use the same ADC with the same resolution, because of the lower dynamic range, then your absolute resolution will go up. Okay? So now let's look at where we can go beyond this just first work. So up to now what we've been doing is doing the unlimited sampling acquisition in software. So we first acquire the signal in the classical fashion with a normal ADC, and then we do the unlimited sampling in software. But the real gain will be provided once you use an actual unlimited sampling ADC. And so these are, for example, prototypes that have been studied in the team of Ayush Bhandari. And so with this, you will be able to show the real gain of that type of acquisition, because you will lower your dynamic range for the acquisition, but retaining the same resolution in your ADC. So in the end, your absolute resolution will go up. Another thing that could be interesting is we're doing this for now. We're only considering the saturation in the acquisition side, but saturation can also happen in the RF side. But maybe using these ADCs, we could lower the gain in the RF chain to avoid the saturation, but maybe make up for it by using this unlimited sampling framework. So this is one thing. Another thing is, here we've only shown like a really basic example of a 1D problem, so just ranging, but we could extend it to a more complex setting, so with more dimension, and also apply it to application where you really see this dramatic change of dynamic range between targets of interest. Another thing is that here we're using the unlimited sampling framework in an encode-decode fashion, in the sense that I encode the signal by doing the unlimited sample acquisition, I decode it by reconstructing it, and then I do the normal processing. But what would be more interesting would be to measure the quantities of interest, for example here the range, directly from the unlimited sampling sample without going through a reconstruction. Okay? So to have something more efficient. So now for the conclusion of this work, so what we've seen is, because of the band limited nature of FMCW radars, and because of the fact that targets have a large dynamic range, okay, unlimited sampling can be used for the reconstruction of those signals. In fact, the reconstruction is so efficient that you can do a live demo of it, so you can do real-time reconstruction. And in the end, I finish by different future work that we are working on. So thanks a lot for your attention. If you have any question, I'll be more than happy to answer them.